All right, you guys, we are going to go over the questions you've been asking me the last couple weeks. So these were the questions from the Friday feedbacks. You can obviously skip through some if you are comfortable with them already. Okay, first of all, how do we convert decimals to fractions to percents in any order? Okay, so I have this awesome chart for you. It should be super helpful. That you can look back to this chart right here. Okay, I also have the explanations in words right here, but I'll just go over a quick example of each of them. So fraction to decimal. Let's say we have the fraction 1/2. Fraction 1/2. Essentially, to get from that fraction to the decimal, think of a fraction kind of like a dividing sign, right? So we're saying the numerator, or the top number, 1, divided by 2. So to get from the fraction to the decimal, we just do the division. Okay, so 1 divided by 2 gives us 0.5. So there's the fraction to the decimal. Now, if we want to go one step further and go from the decimal to the percent, what do? Think about decimal places, right? In percent, if we want to go from decimal to percent, excuse me, all we have to do here is multiply that decimal by 100. Okay, it doesn't matter what the decimal is. It could be like 0.5, it could be 0.05, 0.0005, right? Any of those, if we want to change that decimal to the percent, we multiply it by 100. Okay, so always multiply by 100. So in this case, we multiply by 100, we get 50, and we're just going to tag that little percent sign on there. So 50%. So there we're going from fraction to decimal, decimal to percent. So really you could use this to go from fraction to percent as well. It's the same steps. Okay. Let's talk about percent to decimal. So basically we're going the opposite direction now. So if we want to go percent to decimal, let's say we have 50% and we want it in decimal form. Instead of multiplying by 100 this time, since we're doing the opposite, we're going the opposite direction, we're going to divide. We're going to divide 50% or 50 by 100. So 50 divided by 100, and that is going to give us 0.5. Okay, and then if we wanted to take that another step further and go from that decimal to a fraction, there's multiple ways to do this, but I'll just show you the way that I find the easiest. Basically, if we change the decimal into a percent, change the decimal into a percent by multiplying by 100, so we get 50%. If we put that number, 50, over 100, there's our fraction right there. Now, this is not its simplified form, meaning its most reduced form, right? We know that 50 goes into 50, and we know that 50 also goes into 100. So if we divided both of the top and the bottom by 50, 50 divided by 50 is 1, 100 divided by 50 is 2. So that's the most reduced form. But these two are both equal to each other. Okay, so there's an example of each of those directions. Okay, again, you can reference the explanations here or reference the picture. I hope those help. Okay. Next question. How do you tell the difference between experimental probability numbers and theoretical probability numbers? Great question. Key thing here is that theoretical probability is what we expect to happen, or what what we think should happen. So we haven't actually done anything yet, right? It's just based on thought. Experimental probability, though. Experimental probability is when we're actually doing something. So what actually happens? Okay, so here we're not doing anything. Here we are doing something. Okay, so theoretical probability will always be based on the number of possible outcomes total, not the number of times you actually do something. So what I mean by that, let's say that we have a six-sided dice. Six-sided dice. Okay. It's a fair dice, so it's not weighted. The outcomes here, meaning when I roll the dice, what could I get? The possible outcomes are 1, 2, 3, 4, and 5, and 6. Sorry about that. Okay. Now, theoretically, let's say we want to know the theoretical probability of rolling a 3. In this case, we're not actually rolling the dice, right? We're just looking at how many favorable outcomes there are. So in this case, if we want a 3, if we want to roll a 3, there's only one outcome where we get what we want, right? Only one side of the dice says 3 on it. So the favorable outcomes is 1. And again, this is theoretical probability. And the total number of possible outcomes, again, we already know from up here. Struggling is 6. Okay, so right here, there is our probability of rolling a 3, theoretically. If we were to actually roll the dice, though, again, that's called experimental probability, when we're actually doing something. So let's talk about experimental probability. So what's the experimental probability of rolling a 3? Again, this is based on what's actually happening. So what happens when we roll the dice? Let's say we roll it 20 times. So the number of trials is 20. Okay. And let's say that we roll a 3, let's say 3 times. Okay. So in this case, the experimental probability of rolling a 3 would be the number of times we rolled what we wanted. So the number of times or trials. Doesn't like M's. Number of times it happens, which in this case is 3, over the total number of trials. Number of trials total. And in this case, we rolled it 20 times. So the experimental probability then of rolling a 3 would be 3 out of 20 in this case. So experimental probability is what actually happens. Theoretical probability is what we expect to happen. Okay. All right. Next question. Will theoretical probability be the same every time? This is a great question. It really depends on the situation. So I'm going to give you a couple examples. They're all listed right here under this question. Okay, but I'll just talk you through it. So example 1, let's say we're rolling that 6-sided dice again. We know that there's 6 possible outcomes, right? 1, 2, 3, 4, 5, or 6. Theoretical probability will be the number of outcomes we want. So favorable outcomes, right? Favorable outcomes. Let's go orange. Favorable outcomes over the total possible outcomes. Okay, so for example, if we want to roll a 1, we know there's only one 1 on the dice. So the theoretical probability of rolling a 1 on the dice will be 1 out of 6 because there's 6 possible outcomes. Okay, same as this right here. Now, we'll also get 1/6 for theoretical probability of getting a 2, 3, 4, 5, or 6 because there's also only one of each of those, right? So in this case, the theoretical probability of each outcome is the same, 1/6, 1/6, 1/6, etc. Okay. But let's say we want to know theoretical probability of rolling any odd number on the dice. In this case, there are 3 outcomes we want. 3 outcomes, right? We could get a 1, a 3, or a 5. Those will all be the odd numbers on a dice. So there's 3 of those out of 6 total, right? So in this case, our theoretical probability will be 1/2, not 1/6, right? So it really depends on the situation we're looking at. Another example, example 2 right here. Choosing, let me blue this time, example 2. Let's say we have a marble, a bunch of marbles in a bag. Maybe I can draw you this bag. Let's say we have this lovely bag. We know there's 13 marbles total. 2 of the marbles are green. We're gonna have 5 blue. 1, 2, 3, 4, 5. Where's purple? There's purple. Freaking out for a second. And 6, 2, 3, 4, 5, 6. 6 purple marbles. So 13 total. Here, because because there's a different amount of each color of marble, the theoretical probabilities of getting each color will be different. Right? So this is different from the dice when there is just one of each number. Here, the theoretical probability of picking, let's say, a blue. Let's go back to blue. Theoretical probability of picking a blue marble out of the bag. That should say bag, not bag. Because there's 5 blue marbles, it would be 5. So there's 5 favorable outcomes, 5 blue ones, out of the 13 total, right? But if we looked at the theoretical probability of picking a green marble, throughout the end there, there's only 2 green marbles this time, right? And again, if we looked at the probability of getting a purple one, theoretical probability of pulling out a purple marble, that's also going to be different. It's going to be different than the blue and the green one. It's going to be 6 out of 13, right? So it really just depends on the situation, whether or not your theoretical probabilities will be the same every time, right? On a dice, a normal dice, the theoretical probability of rolling each number is going to be the same. But if the number of different events or objects or numbers of something is different, then your theoretical probability will be different every time. Okay. Why is it that experimental probability gets closer and closer to theoretical probability as the number of trials increase? This is a really deep question. And honestly, it's kind of a hard one to answer. There's a lot of debate on it even still. But and I'm not going to go through this entire example that I've written out for you, this entire thing. Okay. The gist of it though, is the more trials or the more data we have, the bigger the sample size, the more people we're asking questions, the more times we roll a dice, the more data we have, right? The more the theoretical probability, the expected probability, will be equal to the experimental probability. So more trials, I write that up. More trials or sample, more data equals closer experimental probability to theoretical. So if you've ever heard the term regression to the norm, this is what it means, right? The more data we have, the more things balance out in the long run. Okay, so if we wanted to look at the probability of somebody having, the average height, think of the word average, right? Obviously not everyone's going to be the same exact height, the average, right? Some people are going to be below, some are above, but the more data we have, the more those two sides balance out. Okay, I would suggest reading through this example though. It'll kind of explain it a little bit better, and it uses the example of what if we wanted to know the probability of students currently in 7th grade dyeing their hair? Okay, so it might be a little interesting there. Okay, next question. Why is this so hard? Great question. Never feel like you're bad at math just because you're struggling, though. You guys know I emphasize struggling, right? Struggling is how we learn. Some topics are going to be easy for you, some will be harder. Just stick with it, okay? Always let me know if you have questions, though, and I'll try to help where I can. Will we be doing anything else soon or something else soon? Yeah, we're going to be working on probability for another week or two. After that, we'll talk about statistics for a week or two. Probably do a project at the end of that, and then basically just reviewing concepts from the year. Next question. How do you find the experimental probability or relative frequency with a large sample set? The easy answer for this is that it's the same way you would do it with a smaller sample set, right? So experimental probability will always, let me use purple, I like purple, will always be the probability of whatever event you're looking at will be the number of trials the event that you want happened. You're gonna be writing all over this. Over the total number of trials. Okay. Now, probability and statistics will definitely get a lot more complicated than in future grades, than what it is right now. Can't talk right now. But for where you guys are right now, this is the information we need. So no matter what the sample size or number of trials or the amount of data we have, you will always divide the number of times the event you want happened by the total sample size. Okay. This was another great question. If you have 4 colors, how many times would it take to get 25 out of 100 or 25% for all of them, right? So basically what this question is asking is how many trials would it take for the experimental probability of drawing let's say a specific color of marble out of a hat to equal the theoretical probability of drawing that color? The short answer of this is it could take only 4 draws, right? If I was lucky, right? And I drew one of each color in the first 4 draws. Let's say there's 4 different colors, right? 1 blue, 1 red, 1 green, 1 yellow. If I got really lucky and drew one of each color in the first 4 draws, right? The experimental probability and the theoretical probability would be equal after only 4 draws. Okay, that's very, very unlikely though. It's about 0.39%, not 39%, but 0.39% chance of happening. The more we draw, though, the closer we'll get to theoretical probability. All right, next one. How to write the formula for probability? Good question. So probability will always be represented by the variable p. So let's do green. Actually, let's do rainbow. Okay, probability will always be represented by P. P equals probability. Now, the general formula for probability is going to be the probability of some event, right, in parentheses, whatever the event is. So for example, if we're looking at flipping a coin and it landing on heads, we would say probability of it landing on heads. So heads is our event, right? Now, the two different formulas we've been looking at, there's one for theoretical and one for experimental. And the two formulas are given here. Difference again is that experimental is when we're actually doing something, so how many times we're actually flipping a coin, right? And it lands on heads. And the theoretical would be what we expect to happen. Is there a probability for everything? Short answer, yes. There is a chance for any event, even if that chance is equal to 0, right? So let's talk about water boiling. Water boils at a temperature of, I'll draw you a lovely picture. Okay, so we have a lovely pan on the stove, right? Lovely. Ooh, yeah, let's get some flames going. Lovely pan on the stove. I'm gonna go till it's red and orange. There we go. Pan on the stove, a bunch of water in it. Right, there's my water in the pan. Water boils at a temperature of 212 degrees Fahrenheit. In this sentence alone, we could talk about multiple probabilities, right? We could talk about the probability of water actually boiling, right? We could talk about the probability of what temperature the stove is on, the probability of how long it will take, right? So time to reach 212 degrees. We could talk about the probability of water boiling at different degrees, right? Some of these will be impossible, some will be certain, some will be likely or unlikely. For example, it's impossible for water to boil in less than 212 degrees Fahrenheit. But it's certain that if the water is at 212 degrees Fahrenheit or more, it will boil, right? It's also likely, so here's some key probability words here. It's likely it'll take longer for water to reach boiling point when the stove is on a lower heat setting, right? So again, short answer is yes, everything has a probability. Okay, I'll try to get through these last ones quicker. No more drawing pictures. Okay, question. How do you find the difference between theoretical and experimental probability? Keywords here. Difference. Difference in mathematical language means subtract. Right? So really we're just subtract. Really we're just subtracting theoretical probability numbers and experimental to find the difference. Okay? We're just subtracting there. So there's your formula. Why are theoretical and experimental probabilities different? I've kind of already gone over this, but again, theoretical probabilities are what is, I'll highlight this, what is expected to happen, or what we think should happen. This is based on previous knowledge, so if we know we have a fair dice, we know it's not weighted to one side, we know how many sides of the dice there are, or just like intuition, right? We have a coin has two sides. It's a thought or a prediction of what will happen, basically. Experimental probability, though, is what actually happens. So what does happen when we actually do something? It's reality. It's not a thought, it's a reality. It's not a prediction, it's reality. What happened? When we roll the dice, did it actually land on each side an equal amount of times? Probably not. Okay. If there are three possible outcomes, will we still say that there's 50-50, or is it different because there are more than two things? That's a great question. When we say, oh, it's a 50-50 chance, it means that there are two outcomes and they're equally likely to happen. I'm I'm going to highlight that because that's important. It means that there's two outcomes and they're equally likely, right? 50-50, 50% and 50%. For example, if we roll a six-sided dice, we could say that there's a 50-50 chance of it landing on an odd number because there's the same amount of odd numbers as even numbers. If there are three or more options, though, three or more outcomes, we wouldn't say 50-50. If they're each equally likely to happen, and let's say there's three outcomes, there would be a third chance of each. Or if we want to stick with same like percentages, same kind of saying it's 50-50, we could say like there's a 33 chance of something happening. Okay. How do you find ratios to match the problem? Here's just a quick reminder of how ratios can be written. But essentially use the formulas, right? So probability, when we're trying to match the ratio, there we go. We're trying to match the ratio, probability ratio to the problem. Always calculate the probability, okay? And then check if you can reduce or simplify it. So a few of the problems we've looked at in the past, there'll be something like the actual answer is 1/3, or the actual answer is 2/6, but it's been reduced to 1/3 for the multiple choice answer, right? So always calculate the probability and check, definitely check if it can be reduced or simplified. Okay, that's the biggest thing. Will theoretical probability ever be totally reliable? Has there been a time when they are equal in real life? Short answer, yes and no. If we run enough trials, theoretical probability will be reliable. The more trials we do, the closer the experimental probability is to the theoretical, and the more reliable the theoretical probability is. Right? Think about like any psychological kind of things that you've seen, like, I don't know, random things on Facebook, like eat more chocolate and you'll get better test grades, right? If that's actually true or reliable, right, we'd want to have a huge sample set, right? We couldn't just ask two people and say, oh, well, they ate more chocolate than so-and-so and they got better grades, therefore more chocolate equals better grades. No, we want as much data as possible. The more data we have, the more reliable theoretical probability is. Okay, what's the difference between probability of something and the complement? This is a really great question. Basically, the important information you need is in that first sentence, okay? Probability is the chance of something happening, right? The complement would be the chance of something not happening. So probability is happening, and complement is the opposite, so not happening, right? And there's an example and an explanation in here if you want to delve into that. Okay. Well, let's see here. Actually, yeah, let's go over the example really quick. Okay. So let's say that we have, looking at marbles again. We have some marbles. Okay, 10 of them are blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 5 red marbles. That's not red, that's red. 1, 2, 3, 4, 5, and 2 yellow marbles. We're almost done, you guys. 2 yellow marbles. Now, the probability of drawing out a red marble, so probability of red, that says reb, not red. Probability of drawing a red marble, here we go. Because there's 5 red marbles, and we're talking theoretical probability, the theoretical probability of drawing that red marble would be 5 out of the 17 marbles total. Okay, that means that the probability of not getting red, or the complement of red, probability of not getting red would essentially be 17 minus 5, because that's how many other colored marbles there are, right? So in this case, we'd be left with 12. So this probability, or the complement of the probability, would be 12 out of 17, right? So basically, if something is happening, the complement would be how many is left. We're just looking at differences there, essentially. Okay, I hope that answers a lot of your questions. I'll post this paper too, so you can keep looking back at it. All my lovely drawings. All right, hope that helps you guys. Let me know if you have any more questions.